Now we'll look at transfer function and impulse response. This is very similar to what we have studied so far. The transfer function is defined by h of z in z transforms, and it is equals to y of z divided by x of z. Y of z divided by x of z. And then causality. What is causality in z transforms? Causality conditions. A discrete time LTI system is causal if and only if the ROC of the transfer function is exterior of a circle, including infinity, right? For a causal signal, that means right-sided signal. What did we say? The ROC has to be exterior of any circle. The ROC must be exterior of any circle, including infinity, right? It must be exterior to a circle. So this is the condition for causality. If a discrete time system is rational, has a rational transfer function, it is causal if and only if ROC is outside the outermost pole and the order of the numerator is not larger than the denominator. So these are the two conditions for causality. And stability means, for stability, for a discrete time system to be stable, the ROC must include the unit circle. It must include the unit circle. It must include the unit circle. So this is the condition for causality and stability. For a signal to be, for a system to be causal, how should the ROC be? It should be exterior to a circle. It should be the exterior to a circle. ROC of the transfer function of the system must be exterior to the circle, including infinity. Then then for stability, what should we have? The ROC must include the unit circle. Wherever the ROC is, if the unit circle is included in the ROC, then we can say the system is going to be stable. System is going to be stable. If I compare my Laplace transforms and Z transforms, Laplace transform is something like this. I'll have strips, right? I'll have strips in my Laplace transform. I'll have strips in my Laplace transform. So let me say this is my sigma and this is j omega, and this is Z transform. In Z transforms, this is my imaginary part of Z and this is the real part of Z, right? The right hand side in the Laplace domain, in the S domain, the right hand side in the S domain will be inside the circle. It corresponds to the area within the circle, and the j omega axis in S domain, the imaginary axis in the S domain, corresponds to the unit circle. The right hand side corresponds to the inside of the circle. The right hand side corresponds to the outside of the circle, and the left hand side of the S domain corresponds to the inside of the circle. It corresponds to the inside of the circle. So this is Laplace domain, S domain, and this is Z domain. This is how the axes are transformed in between S and Z domain. So whatever is there on the imaginary axis in S plane is there on the unit circle in Z domain. On the right hand side in the S plane is outside the unit circle in the Z domain, and on the left hand side of the S domain is inside the unit circle in Z domain. Now we'll comment on the causality and stability of a system. when this is the transfer function of the system. Now, the transfer function is given. We have to comment on the causality and stability for three different ROCs. First, mod z is greater than 2. Mod z is greater than 2. That means the ROC is right sided, right? It is outside the circle. It is outside the outermost pole, right? How many poles are there here? This I can write as z by z minus 0.5 plus z by z minus 2. So there are two different poles, 0.5 and 2, right? This is 0.5 and this is 2. So 0.5 and 2. So outermost pole is 2. When mod z is greater than 2, that means it is outside the outermost pole. That is right-sided signal, which means the signal is causal. Since the signal is causal, so I can comment on the stability that my given system is causal or the signal is causal. Then I have to comment on the stability also, right? To comment on the stability, this is my ROC, right? Mod z greater than 2. Where is my mod z equals to 1? Mod z equals to 1 is, this is 0.5 and this is 2. So my mod z equals to 1 will be somewhere here, right? This is my mod z equals to 1, my unit circle. So is my mod z equals to 1 included in the ROC? No, it is not included in the ROC, right? It is not included in the ROC. So the system is called unstable. The system here is unstable. The system here is unstable, right? So similarly, we'll consider the other ROC, mod z less than 0.5. Now when mod z is less than 0.5, when mod z is less than 0.5, so where will the ROC exist? The ROC exists inside the inner circle, inside the inner circle. It's not going outside the inner circle. So if it is inside the inner circle, which means ROC is left-sided and the signal is anti-causal. So the comment on the causality is nothing but the system is anti-causal and its corresponding h of n, the impulse response is this. And now the unit circle is not included in the ROC again, right? The ROC is less than 0.5, but the unit circle is outside 0.5. So it does not include the unit circle. Again, the system is unstable. The system is unstable. Now for the third and final ROC, for the third and final ROC, and this is the 0.5 circle and this is the 2 circle. My mod z is in between 0.5 and 2. That means here, right? It is here. It is in between 0.5 and 2. So if it is in between 0.5 and 2, then the signal is two-sided and the signal is no, the ROC is two-sided and the signal is causal, non-causal signal. The corresponding h of n will look like this. And now since the unit circle is included in the ROC, it is present inside the ROC. The unit circle mod z is equals to 1, right? The circle shown in the orange color, it is included in the ROC. So the system is said to be stable. This is how we'll find the stability of the system using Z transform. Using Z transform. The final topic in the Z transforms is solutions to systems with difference equations. So we'll have the difference equations for the given for the system LTI systems, and we'll have to find the solutions to those systems. So this is the difference equation that is given for the system, and the input x of n is given, and there are some initial conditions that are given. So from this we need to find the solution to the system, that is we have to find y of n. So first we'll have to find y of n. So first from x of n I'm going to find x of z. X of n is in the form of a power n u of n. So the standard Z transform pair is a power n u of n has the Z transform Z by Z minus a with mod Z greater than a. So since a is equals to 5, my X of Z is Z by Z minus 5, Z by Z minus 5 with mod Z greater than 5, right? Now I'll take this difference equation and apply Z transform. I'll apply Z transform. So what will I get if I apply Z transform? Y of Z minus 0.5 into what is the Z transform for y of n minus 1? Y of n minus 1. What is the Z transform? We'll consider the unilateral Z transform or one-sided Z transform. One-sided Z transform. The corresponding Z transform is y of Z into Z to the power minus 1 plus y of minus 1 plus y of minus 1, and on the right hand side I have x of z. Now I'll take y of z common on the left hand side, then I'll have 1 minus 0.5 z inverse, and in place of y of minus 1 I'll substitute 2. That means I'll have plus 2 here, right? I'll have plus 2 here, right? I'll have plus 2. Then I'll have plus 2 multiplied with minus 0.5, that is minus 1. That is, I'll have minus 1 here. This minus 1 I'll take it to the other side and I'll make it plus 1. I'll make it plus 1. Now I'll simplify this, and in place of x of z I substituted whatever I found for x of z. Right, now I'll find y of z. I'll simplify for y of z. So this is my y of z, right? Y of z. So 2z minus 5 divided by z minus 5 and 1 minus 0.5 z inverse. Now this z inverse I'm converting it into form of z. This is nothing but, I can write it as, if I multiply by z and z, what happens? Z into 2z minus 5 divided by z minus 5 into, I'll multiply these two, that is z minus 0.5. This is my y of z. That is my y of z. Now I have to apply inverse z transform to y of z. So what I will do here is, I will consider y of z divided by z, and I'll apply partial fractions. The same procedure which we followed for partial fractions while we are discussing inverse z transform, that we'll do here, and we will finally find the inverse z transform, right? Inverse z transform. Since the input is a causal signal, we are going to get the output as also a causal signal, right? That is how we find the solution to the given system. The next question, this is the difference equation and the input and the initial conditions. Now we have to find the system response, y of n. Similar to the previous problem, first we have found the z transform of the input, and then we are applying z transform to the given difference equation, and we'll substitute the values of y of minus 1 and y of minus 2, and we'll solve for y of z. We'll substitute the value of x of z which we have found out here, and we'll find value of y of z, right? So this is the value of y of Z. Now we'll apply partial fractions. To apply partial fractions, I have to consider y of z divided by z. I'll consider y of z divided by z, and I'll apply partial fractions and solve for values of a, b, and c. Now I'll substitute the values of a, b, and c and find the corresponding inverse z transform. I'll find the corresponding inverse z transform. Here, if you look at this, these two terms, we can find the inverse z transform directly, right? It is in the form of z by z minus a. Now in this term, we have z by 3z minus 1. We have to get this into the form of a regular z by z minus a. So what I'm going to do is I'm going to take 3 common in the denominator. Then I have z by z minus 1 by 3. So now this is in the form of z by z minus a. So I can apply the same inverse z transform. Right? When I apply z transform, inverse z transform, this is what I'll have as my final inverse z transform. This is the response of the system for difference equations, right? With the solutions of the system with difference equations. So this is the end of unit 5.